Okay, hi. Welcome to the first slideshow that I'm going to post for those of you who are completing the course under these very trying, weird, unusual circumstances. So let's see how this works out. I look forward to your comments. Please email me what worked, what didn't, and so that I can try to improve any of the other slideshows that I might do. So for chapter 26, I'm going to post 2 or 3 slideshows, not covering all the topics in chapter 26, but some of the key ones. And so in this video, I'm going to cover astronomical standard candles and Cepheid variable stars and the extragalactic distance scale. So here we go. Okay, so astronomical standard candles. This is a gorgeous graphic from NASA and the Jet Propulsion Laboratories that illustrates the idea of standard candles. But first, kind of curious thing with the textbook is it doesn't use the word standard candle, it uses standard bulb, which I guess is their effort to use something, a word that might be more current than candle, but everyone in the astronomical universe says standard candle, and that's the language that we're going to use. And so the idea is, suppose we want to figure out how far away some object like a galaxy is. Well, if that galaxy contains a kind of astrophysical object whose luminosity you can know in advance, luminosity, the amount of energy that it radiates out into space. That's what we mean by standard candle, is that if we can be certain we know what that thing is, then we can compare how apparently bright the object is, let's say this candle far away, with this candle nearby. And the fact that this one would be much fainter than that one would directly tell us that this one, how far away it is. There's a similar idea in perspective. Here's like a standard kind of half-sized ruler. And if you think of this as a standard ruler, you say, well, that one, if it is the same rulers, the same variety, then it would look smaller simply because it's further away. Okay, so we have to recall some concepts that we saw back in class, I think about the week before our last week together, and it's been a long time, so you might want to review some of these things from our previous lecture slideshows. 2 concepts in particular. The luminosity, which we define as the energy emitted per second by some object radiating out into space. And we distinguish between luminosity, which is an intrinsic property of the object, with what it looks like to us, its apparent brightness. And that's set by 2 things. One is the luminosity, and the other is how far away it is. The farther away it is, the fainter it's going to look. And here's a graphic that I showed you. This comes from chapter 5, but it's actually something we got to when we were doing the HR, the Hertzsprung-Russell diagram. And this is a graphic to convince you of the nature of the inverse square law. So let's put this light bulb over here, as I have, and let's follow some rays. And you say, well, these rays happen to cross a square of a given size on this first sphere. Then the rays would cross 4 squares on a sphere twice as large and 9 squares on a sphere 3 times as large. So in this case, for example, that means the energy is cut by a factor of 9. The apparent brightness is cut by a factor of 9 on any one of these squares compared to what it would have been back there. And that's the origin of the inverse square law. Now, the way in which we use this when we were heading towards building the HR diagram is we wanted to know the luminosity of stars. Before that discussion, we only knew their color, and from that we could then deduce their temperature. For everything else, we needed to start with the luminosity, and that meant we had to figure out the distance to objects. We could measure that distance, and that is very, very hard. And what we talked about at the time was parallax, the analog of stereoscopic vision. So you used parallax for stars to figure out their distance. Then you did something which is relatively easy, which is just measure how does it look to us, and then one could infer their luminosity, an intrinsic property, how much energy does that thing radiate per second. And after that, we were able to figure out many other things, the size, the mass, many, many other properties. We're going to play with this formula now in a different way. This time, we're going to assume that we already know the luminosity. That is to say, we have some object that is a standard candle, just like this standard 60-watt light bulb. If we know the luminosity, and as before, we measure the brightness as it appears to us from here, which is relatively easy, then we can infer the distance. And that's the goal now, is to find out the distance to things that are so far away that, for example, parallax will completely fail in terms of a direct measure. Objects, galaxies, there is no other way but an inference of this kind that will let us determine their distances because, well, the distances are so great. Okay, astronomical standard candles. For an object or a class of objects to be considered an astronomical standard candle, their luminosity or luminosities must satisfy three criteria. One is that the luminosity should be the same for all objects of a given type. Say by analogy, we would want to know if we're looking at a light bulb that it is in fact a standard light bulb of the 60-watt variety. We'll want to be able to infer that we are in fact talking about a particular kind of object from something among its properties that is easy to measure. We're not going to be doing the direct distance measurement because that's simply too hard, if not impossible. We want something else that's easy to measure that will be a stand-in for distance by telling us, yes, this is one of those standard candles. So we'll see examples of what those measured properties are coming up shortly. And we want the luminosity to be large enough that we can see these or detect these things at great distances. And in fact, in astronomy, we need more than one kind of standard candle because there are, for instance, galaxies that are nearby, galaxies that are intermediate distance, galaxies that are clear across the universe. And a given kind of standard candle might be useful for nearby galaxies, but not for more distant ones. And we are, in fact, very lucky. Nature has provided us with a number of what I like to call lucky breaks, several different kinds of standard candles that have proven to be very useful. And the two examples that we're going to consider here are Cepheid variable stars and then white-dwarf supernovae, which in a textbook are usually referred to as type 1a. And I'll get into what this title means a little bit later on. Okay, Cepheid variable stars. Historically, Cepheids were extremely important, providing us with two major discoveries in the early part of the 20th century. First, they provided us with a first accurate estimate of our location in the Milky Way galaxy. For centuries, it was thought that we were at the center of the Milky Way, where in fact we are about halfway out from the center. And Cepheids, or for variation on Cepheid variable stars, were key to making that first determination. And maybe even of greater importance historically was the use of Cepheids by Edwin Hubble to make the first estimate of the distance to another galaxy. And I'll come back to why that was such a surprising thing at that time. So Cepheid variables are, as the name suggests, variable stars, or many kinds of variables, that stars that change with brightness for various reasons. In the case of a Cepheid, the brightness varies in a cycle with a period that ranges from a few days to weeks, even a month or two. And these things can be extremely luminous. And the fact that they vary in brightness in a characteristic way makes them act like beacons. They're so bright and they almost flash in kind of in real time. We see can therefore make them out in galaxies that are far away. And so as the animation suggests here, these things change in size with time. We call them now pulsating variable stars. It was not known for decades what these things actually were physically, but the key relationship of interest to astronomers was discovered, as I said, kind of before we understood what they were. And this relationship is between the luminosity of a Cepheid and its period. Now, there isn't a single luminosity because the Cepheid is changing with time, so one should really think about, say, the average luminosity. And so today we understand what's going on quite well. Here's a kind of simple but nonetheless useful argument. Suppose you have two Cepheids, one, let's say, that's on average is bigger than the other. Well, you might guess naively that the bigger Cepheid should on average be more luminous, since there would just be more of it to radiate energy into space. And likewise, if it's bigger, you might expect it to take a longer time for it to pulsate, simply because it has to travel through a larger distance as it does so. And that leads to this idea of relationship between the period and the luminosity. And that is represented in this graphic from the textbook. This plots luminosity in relationship to the luminosity of the sun. Again, this is the average luminosity versus period. It shows Cepheids at another kind of variable star that's similar to but slightly different from Cepheids are our Lyrae stars, which were used for the Milky Way location determination. Anyway, so this relationship, as I said, its origin, physics reasons for it were not understood when it was discovered, but nonetheless it could be used. The person who discovered this period luminosity relation is a heroine of early 20th century astronomy named Henrietta Leavitt, and this relationship is sometimes referred to as Leavitt's law in her honor. So Cepheids qualify as standard candles, not the luminosity changes with time, of course. The average luminosity is different for different periods, but nonetheless it's a standard candle because you find the period and you know the luminosity. And it's scattering points here indicates that there are some uncertainties, but we won't get into that here. So you infer the luminosity from something that is relatively easy to measure, which is the period. And as we saw with this graphic, you compare with the apparent brightness, and then you know the distance from the inverse square law. And very importantly, Cepheids can be so bright, so luminous, that we can spot them in other galaxies. Not the most distant galaxies. These are identifiable within galaxies that are relatively close to the Milky Way. We'll need other standard candles to get out to more distant galaxies, but nonetheless these are extremely important. So here's a very short video that kind of captures the essence of this whole argument in short form, and I think it's quite clear.
Most normal galaxies contain a class of variable stars that act like beacons to help determine the distance to the star and hence the galaxy. First, the pulsation period of a Cepheid variable star is used to infer the absolute brightness of the star. Then, comparing this to the apparent brightness, which is easily measured, astronomers can determine the distance to the star. This yardstick then provides an estimate of the distance from Earth to the distant galaxy housing the Cepheid.
So just a little sidebar, this animation showing the Cepheid variable pulsating, for years and years I wondered if it might be possible to make measurements of this kind using a relatively small telescope like the one that we have here at SFU. I thought, fantasy, it'd be cool if I could create a real time-lapse video showing a Cepheid pulsating, and in fact, yes, we've done that. And I'll post a separate video for you to have a look at, which describes this really beautiful group project that was done by a group of students and local amateur astronomers at the observatory. I think it was really quite an exciting study. And yes, you'll find some animations, time-lapse videos that I made just like this one. Okay, so here is an actual image of a spiral galaxy. I think this is called Messier 100. This is taken by the Hubble Space Telescope. This contains lots of Cepheids. They're showing you just one of them, which is located here out near the edge of the galaxy. And here is the brightness over a period of days. Say, call this day 1, brighter on day 6, still brighter on day 28. I think this it takes a couple of days before it then returns to this original brightness and repeats the cycle all over again. One thing that is not so important for us, but I thought I would mention, is that if you plot the brightness of the star, the Cepheid versus time, you get a variation because it is a variable star. The curve traces out a very characteristic we call a sawtooth. And this pattern, if you plot a variable star's brightness and you see a sawtooth, it's a pretty strong sign that you are in fact talking about a Cepheid variable. So Cepheid variables were used by Edwin Hubble to make the first determination of the distance to a galaxy, and thereby the first person in history to set the true scale of the universe as a whole. And he used Leavitt's law, discovered by Henrietta Leavitt, to do that. Unfortunately, Leavitt did not live long enough to see her discovery used in one of the most profound revelations in the history of science. Here's a picture of the Andromeda Galaxy. We've seen this before in this course. It's a gorgeous image taken by an amateur astronomer. Today you look at this thing and you say, galaxy. It kind of seems obvious. But in fact, the nature of these things was debated for centuries. And why would you think this would be so mysterious? Well, here is an artist's impression of a solar system in formation. And we talked very briefly about how this works. A giant cloud of gas and dust collapses into a pancake with a star forming in the center and planets in the periphery. Well, the formation of a galaxy is kind of the same process on a much larger scale. And so some astronomers looked at this and said, aha, this is a star forming in a cloud of gas and dust, and there are planets, maybe we can't see them yet, in the disk surrounding it. Whereas other astronomers thought, no, this thing is completely different from that, and it's a separate entity from our own Milky Way galaxy. And to really resolve this debate, in fact, today it's referred to as the Great Debate, which continued right up until the time that Hubble made this first determination of the distance. This great debate was one of the central things in astronomy, and it really required determining the distance to settle this question. Knowing the distance is essential, just as it was essential to know the distance to stars before we could figure out their true properties. Likewise, we had to know the distance to this galaxy before we could know what it really is, and the modern estimate of that is about 2.4 million light years. Once you know the distance, you can then decide, okay, this thing looks pretty small on the sky. It's about the same size, apparently, on the sky as the moon. But you say, is this because it's relatively small and nearby, or is it huge and far away? Well, it's far away, and therefore it's huge. So knowing the distance tells you that from the apparent angular diameter of Andromeda, you determine its true size. And so it's 100,000 light years or so end to end. This is not a single star formation, but an entire island of stars. And then you look at the sky and say, this thing doesn't look very bright from Earth, but of course its true luminosity depends on how far away it is. Well, from this tremendous distance, the apparent brightness is low because of the distance. In fact, the apparent magnitude plus the distance tells you that this thing contains hundreds of billions of stars. The luminosity of the galaxy as a whole is equivalent to that of hundreds of billions of stars. And so this amounted to an absolutely revolutionary transformation of our conception of the universe. For the first time in history, we knew what had been previously referred to as a spiral nebulae were in fact islands of stars, similar to the Milky Way, and astronomers had already cataloged hundreds of thousands. Today we know of millions and billions of these things, and so it really changes our scale in terms of what's going on in the universe as a whole. Okay, so the second of the two standard candles that we're covering for this course is a category known as White-dwarf supernovae. I'll come back to this more technical name in just a second. And so as a Cepheid, White-dwarf supernovae turned out to be an extremely important standard candle. And in fact, for determining the distances to the great galaxies at the greatest distance from us, white-dwarf supernovae are basically the tool of choice. And so we've talked about supernovae before. Those supernovae that we talked about before were those related to the collapse of the core of a massive star. When the massive star dies, as we saw, this core suddenly collapses. There's an implosion followed by an explosion, and this leaves behind one or two possibilities: a neutron star or a black hole. So for historical reasons, core collapse supernovae are referred to as type 2. This other category is type 1, and there are several subcategories, and we won't get into all of that. And so what are white dwarf supernovae? Well, white dwarf supernovae involve a binary star system. So that would be two stars, one of which, let's say, was a star like the Sun, that died and turned into a white dwarf, with the other star continuing to live out its main sequence life. If these two things are close enough, then the powerful gravity of the white dwarf can draw material off from the partner star, which then spirals inwards and can land on the surface of the star. And so what happens to the material as it goes into the white dwarf? Well, it falls into an enormously deep gravity well. Remember, this thing has the mass, something like that, of the Sun, in a region the size of a planet like the Earth. And so that's an incredibly deep gravity well, and as the gas goes screaming into the gravity well, it gets heated up to very, very high temperatures, and by the time it lands on the surface, the temperatures can be so high that that material, mostly hydrogen gas, fuses and into sort of like mini hydrogen explosions, and these things can occasionally turn into what we call novae. They can brighten and then dim again. However, if the mass lands on the surface and stays there and builds up to a certain point, then in fact the star can be completely destroyed in what we refer to as a white dwarf supernovae. Okay, and this you have to recall the Sandra-Shekar limit, this weird quantum degeneracy pressure that sustains the enormous mass of the white dwarf. There is a limit to that. Okay, this goes back now what seems like a lifetime ago. Upper limit 1.4 solar masses. So if material spirals in and lands on the surface and manages to stay there long enough, then the mass can reach this critical limit. And then if it does, something very different from a core collapse occurs. The entire star, the entire white dwarf, suddenly undergoes a sudden thermonuclear detonation and is completely destroyed. Now, what makes this white dwarf, a supernova, a standard candle, is it's basically a tipping point. Either you reach that amount of mass that's necessary for the destruction of the star, or you don't. And once you do reach that limit, if you do, then it's a sudden and spontaneous detonation with basically nothing left behind. And so this European Southern Observatory video mode to play for you is very short, very sweet, captures the essence of what's going on. Okay, a natural question I'm sure you're asking is what happens to the partner star? Well, it turns out that the partner star can, depending on the details, survive the explosion, which seems kind of astonishing. But nonetheless, it's true. Okay, so standard candle distance indicator. What makes these things standard candles is that all blasts have essentially identical luminosities because of that tipping point nature. Either you accumulate enough mass as the white dwarf from the partner, or you don't. And this is now the detonation of an awful lot of mass. And so these things are bright enough to be seen from tremendous distances. In fact, the detonation of a white dwarf supernova can produce a result that is as luminous as an entire galaxy of stars. This is a gorgeous, gorgeous image that I've taken from the textbook. This is a white dwarf supernova on the edge of this galaxy. And so just as with core collapse supernovae, white dwarf supernovae can outshine the host galaxy for periods of weeks or even a month or two. And this is what makes them visible from such tremendous distances. That brings me to the end of this first video slideshow. I hope it proved useful. Please do send me comments by email, what you found useful, what you think could be improved. And I'll be posting video number 2 on Hubble's Law and the Expanding Universe a little later. So until I see you again, take care.